Hi, I'm Brian Dunbar, your host for this educational video series that provides technical background for the innovative series called Heart of a Building. I help to direct the Institute for the Built Environment at Colorado State University. In this episode, we'll delve into the topic of energy efficiency, starting with the important concept of building as a system. I'll include instructional videos from 3 great projects that we highlighted in the first Heart of a Building episode. By the end of the video, you will gain knowledge on building envelope systems, R values and U values, insulation, and ground source heat pump systems. Each of these elements played an important role in the projects featured in Heart of a Building. You'll gain an understanding of how each subtopic can contribute to the overall energy efficiency in any building. Well, before we dive straight into the energy efficiency subtopics, let's start at the very foundation of these projects. Almost without exception, our best performing buildings start with the concept of building as a system. When we say building as a system, think about the insulations used, the wall and roof materials, the windows, natural light, natural ventilation, efficient electrical equipment, and efficient heating and cooling systems. Amory Lovins from the Rocky Mountain Institute has always professed that we shouldn't think of each component in isolation. Instead, consider how each piece contributes to a superior whole and maximize that system. Amory has said the only moderately more efficient house and car do cost more to build. But when designed as whole systems, the super efficient house and car can often cost less to operate than the original unimproved versions. Amory has demonstrated this understanding in a housing development in Davis, California, and also in his own home in Aspen, Colorado. In both cases, a hot climate and a cold climate, his teams were able to build comfortable houses without heating and cooling systems. As Amory alludes to, it's important to understand how each component contributes within a coordinated system so that the integrated whole building design approach can be developed. When we talk about building as a system, we should also assure that the building provides occupants with comfortable and safe and attractive living and working environments. Successful planning results require superior architecture and engineering designs and quality construction practices and intelligent operation of the systems over the life of the project. Well, in addition, it's important to remember that different climates require regionally responsive designs and equipment. Suffice to say, our best performing buildings for energy, comfort, security, and health are treated as sophisticated, interrelated systems. A building envelope is the physical separator between outdoors and indoors, including the resistance to air and water and heat, light, and noise transfer. All told, the building envelope components work together to perform 4 basic yet critical functions. First of all, moisture management. Second, temperature regulation. Third, structure stability. And fourth, controlled airflow. Airtight construction quite simply means that there are no unintended gaps or openings in the building envelope. that would allow air along with heated molecules to leak in or out of a building. The building envelope includes the sets of materials that comprise the foundation, the walls, roof, windows, and doors. The connections and compatibility between all of these elements is critical to ensure that the building envelope functions as intended. A tight building envelope allows for the high level of control over temperature and humidity levels, indoor air quality, and energy consumption. And this requires extra attention to insulation, caulking, the adhesive tapes and sealants, and energy efficient windows to acquire that tight shell for the building.
So all of these airtightness membranes and tapes are vapor open. We want that insulation to be able to stay dry.
Beautiful. Yeah. Everything you've chosen is something that, is it like smart membranes or is it just always vapor open?
Yeah.
What I mean by a smart membrane, I'll just state that like some technologies allow at different temperatures or different humidities, I guess, to allow vapor to transfer. So tell me
Our
about that.
membrane that we use on the inside of the walls and the ceilings is a smart membrane.
Okay.
It will allow the vapor to escape.
Okay.
If you apply it the right way, right? You
Okay,
can't turn it around.
Right.
And then
Yeah.
it won't let humidity from your showers, for example,
Go in.
go in.
Beautiful.
So this is that problem, and I think one of the defining principles that we learned from Katrin Klingenberg,
Who started Passive House.
2010,
Right.
yeah,
Right.
was that we need to avoid vapor sandwiches.
Right.
So a quick demonstration of a vapor sandwich is ice and water shield on one side of OSB decking and then spray foam on the very other. Now that's a vapor sandwich, and this is okay with code. So in the next 15 years or so, this is going to be an increasing situation that we're looking at. But so that litmus test right there, we creating a vapor sandwich. So we use OSB because it's vapor open, or it's a vapor control layer, and that's what we really want, is vapor to be controlled. We want it to be rejected in its bulk form, and then when the sun shines on it, we want it to release that molecular structure out into the ambient air and not stay within the cavities.
Well, as you can see, the importance of an airtight envelope lies in its ability to improve the comfort levels inside a building and improve the energy efficiency of the entire building, plus a reduction in moisture infiltration levels. A refresher on the 3 heat transfers could be helpful at this point. Remember back to your high school science class or a professional course that's focused on energy. Where do heated molecules go? Well, heated molecules move to cooler places, and those molecules move in 3 ways: convection, radiation, and conduction. You might remember that convection is heated molecules moving through the air. So a forced air heating system uses this heat transfer. Radiation is heat from sources such as the sun or a light bulb or a fireplace, where the heated molecules radiate from the heat source to another solid, such as your skin or a brick wall or a pool of water. Think about when you've walked near a brick wall or a walkway after sunset. You feel the heat radiating off of those bricks. And the third heat transfer method, conduction, that's what insulation is mainly focused on. And our best insulated walls and roof systems significantly slow the heated molecules as they try to move in or out of a building. On a hot summer day, heat molecules move toward cooler interior space, while heated molecules seek a cooler exterior on cold winter days. Well, talking about the heat transfers, that's a perfect lead-in to discuss the importance of meticulously ensuring that there are no open edges, or cracks between windows and walls, imperfections between the roof and the walls or between the walls and the foundation. Back to that notion of building as a system. The building's envelope isn't tight if we haven't ensured that all joints and gaps are tightened. When the envelope is tight, we've slowed convection. And of course, we need to include sufficient insulation all around the envelope to slow the conduction. A discussion of insulation types and uses is a good topic for its own video course, but yet I want to briefly mention that the insulations incorporated into our highlighted projects certainly play a major role in building energy performance. Let's listen to Paul ask Cody and Lisa about the insulation in their Greenspire project.
And then the walls, you got 2 inches of rigid, so XPS, is that correct, on the outside?
EPS.
EPS, okay, yeah, so expanded polystyrene on the outside, so
Yes.
good. So that's like about an R8, is
Yep.
that okay on the outside? Then what do you have in the wall cavity?
Cellulose.
Cellulose again, excellent. Okay, so filling the cavities to about an R29, 30, you know, in that range, beautiful, okay.
Exactly.
And then underneath the crawl space, what do you have there?
Insulated floor system.
Oh, okay, cool. What's the
We-
insulation in that? Or just refresh my memory on that, or refresh the viewer's
I
memory.
think it's cellulose also.
Is it cellulose there too? Okay.
Yeah, I think the cellulose argument's a really good one. And that's something that can change in the field. I mean, it's common that as pass-fail we'll spec cellulose or something and we'll end up with blown-in fiberglass or something.
Okay.
We like cellulose because it's a recycled material and it's very anti-rodent and buggy.
I agree, yeah.
But we'll see with that. but-
Fiberglass rodents don't have a problem with, but cellulose, they don't like it, the borate that's on there, yeah. So that's
Yeah.
good, yeah.
But dense packing it in, then it'll surround all the wiring and everything, which is why, you know, it's very tempting on this, you know, you'll see bats in normal situations go and slap them in, but then you have little air pockets, and that's the other part of our science is we don't want any air pockets in any of our
Right.
assemblies. This is how we do it.
Interesting thoughts shared about how rodents are more fond of fiberglass than cellulose. As I mentioned, we'll have a future episode that specifically focuses on insulation. But before we leave the topic, I want you to see a seldom used insulation system that Con Frank employed in his exemplary home. Let's listen to Con as he discusses the virtues of the insulated concrete form system.
Started building the home for the envelope, so the thermal envelope for it. Tell me some of your choices and why you chose them, so we can start foundation to the walls going up. That'd be great.
We evaluated the conventional construction, which everyone has done for many, many years. We evaluated some of the SIPS panel stuff. We did the ICF. The ICF is one of the features that's in here that cuts down the air infiltration and creates a thermal mass better than any other process that I know.
So pause just for a second. So an ICF insulated concrete form, it's going to have, in your case, it's got 4 inches of foam,
2 5/8 on each side.
2 5/8, okay, on each side, and then concrete in the middle.
Yes.
Poured in on site. Yeah.
Right.
So,
And so we're insulated concrete forms all the way to the trusses. We have high-heeled trusses. And so we sealed all the trusses from the concrete up to the baffles, up to the airspace for ventilation in the attic
Right.
with foam. So that is all sealed because that's the biggest culprit in air infiltration in the house. Heat transfer and air infiltration. And so we kind of covered all these little details.
Well, Con's home is certainly performing well. You might consider using insulated concrete forms on a future project. This brings us to our next topic, our values of all the building components and U values for windows and glazing. As is commonly known, the higher the R value, the better the insulating properties and the better the thermal resistance. Let's listen in as Lisa Farmer discusses the well-planned R values for their project.
So Lisa, you've told me rules of thumb for passive house, the idea of an R40 underneath, an R50 on the walls, R60 for the ceiling or attic. For Greenspire, you're really close to that, but what'd you end up using and then why?
We are very close. We're about R38 where the floor meets the crawl space.
Nice.
And then the walls, we did push for a little bit more rigid insulation than we got. So we landed at a R30. Okay. We have 2 inches of rigid foam on our framed walls.
Nice.
And then the roof itself is a R60 as well.
And that's on the roof deck itself, or where is it, on the attic level?
The attic level.
Attic level, okay, cool. What materials are you specifying for it? Let's start at the attic. What's going to be in the attic for the insulation type?
We have got the R60 is 18 inches of cellulose up in the truss spaces.
Okay.
And the top level, we'll use the Intello membrane that we talked about for the air tightness level.
Okay.
And then each of the units is airtighted itself from each other.
National, local, and international codes continue to require higher and higher R values. Yet these 3 projects decided to soar above the code when it served their performance goals. And you may know that R values are not typically used as a measurement of glazing products. U value, which is also known as U factor, it's a measure of heat transfer, especially heat gain or loss through glass. U value is a calculation of the conduction properties of various materials used in the construction of windows and doors and skylights, what the industry typically refers to as fenestration. Lower U values indicate decreased heat transfer. And there's a mathematical way that R and U values relate. The U value is the reciprocal of the R value. In other words, U equals 1 over R and R equals 1 over U. For example, a material with an R value of 5 has a U value of 0.2, which relates to a well-insulated window. So let's watch Lisa as she talks about their airtight window and also the performance of the glazing.
And what about the windows themselves, Lisa? So it's like
Yes,
yeah.
these were the windows we were talking about. They're less than 0.2. This one's 0.5. It's fixed.
Yeah,
the operable one
0.15, yeah.
is
0.17. That's
0.017, yes.
Those are excellent windows. Like Energy Star in our area requires about a 0.3
Yes.
approximately. So a much
Less
better
than
window.
0.2 is where we're targeted.
Yeah, that's a great window.
So you hear Lisa talking about even better than 0.2. Con Frank is rightfully proud of the windows in his home. Listen to him speak about the U values.
You happen to know the U value of the windows that you installed?
The fixed glass in here were 0.20.
Okay.
The operating glasses were like 0.21 and 2.3.
Extremely good. And then, as I understand it, you did some different solar heat gain coefficients with the glass on the south side versus other sides of the home. Is that correct?
We very specifically picked glass that will allow solar gain for us in the wintertime.
Nice.
And so we can have quite a bit of solar gain, BTUs of solar gain in the wintertime, and in the summertime, the R value or the glass reflects it off, and we don't get much gain out of it.
I'm going to guess, you tell me if I'm in the ballpark, I'm going to bet the windows on the south side are letting in 55 to 60% of the sun.
56.
56, good. I'm in the ballpark. That's good. Good. And then on the other sides of the house, probably only 25, maybe 30%?
I think we're at 31 or 32.
Okay.
To further understand energy performance ratings for windows, it's important to also mention solar heat gain coefficient. The solar heat gain coefficient is the fraction of solar radiation that's emitted through a window or door or skylight. And it's either transmitted directly or absorbed and subsequently released as heat inside a home. The lower the solar heat gain coefficient, the less solar heat it transmits, and the greater its shading ability. Now we're going to move on from the building envelope and the U and R values to introduce today's final energy efficiency topic, ground source heat pump systems. A ground source heat pump or geothermal system is a central heating and possibly cooling system that transfers heat to or from the ground, often deep in the ground. Ground source heat pumps are used for space heating and cooling and are also used for water heating. The benefit of ground source heat pumps is that they use and concentrate naturally existing heat rather than producing heat through fossil fuel consumption. The system includes three main components or subsystems. First of all, the earth connection. So we're using the earth as a heat source and sink with connected pipes, and it's commonly called a loop, and they're buried in the ground near the building. The loop can be buried either vertically or horizontally. It circulates a fluid, water or a mixture of water and antifreeze, that absorbs heat from or relinquishes heat to the surrounding soil. The second subsystem is a heat pump. For heating, a geothermal heat pump removes heat from the fluid in the earth connection, concentrates it, and transfers it to the building. For cooling, the process is reversed. The heat pump will absorb the heat from the building, transfer it to the fluid, and then on to the earth. The third subsystem is heat distribution. Conventional ductwork is generally used to distribute heated or cooled air from the geothermal heat pump throughout the building. The first Universalist church built a model to demonstrate to their members how a ground source heat system would work for their renovation. Let's listen to Milt talk about the church's system, why they chose it, and how well it's working.
It's probably one of the best kept secrets in the energy area. But heat pumps have been around for a long time, and anyone that has a refrigerator in their kitchen has a heat pump. Right. So the technology is over 100 years old. Mm-hmm. But what happens is these pipes that circulate water in the ground then become at ground temperature, which is constant. Once you get below the frost line, it's about 55, 60 degrees year-round.
In Colorado.
In Colorado, right. If you go south to Florida, it's warmer, obviously. Right, yeah. But still, right. If your building has excess heat in the summer, you put that heat into the water, circulate the water into the ground, and it is returned to 55 degrees. So it comes back out and into the heat pump furnace, which then takes the hot air and transfers it through a heat exchanger into the refrigerant, and that refrigerant is cooled and puts the heat into the water. It goes back into the ground, and you just have a closed loop system. You're not using any water. Right. You're just using the water as a medium to transfer the heat. In the wintertime, you literally turn on a reversing valve and draw heat out of the 55-degree water, right, and pump it up to about 90 degrees, and then it heats the air that's going into the rooms of the building. Yep. So it's a very ingenious technology. It's well known, well studied, and low risk, and
Exactly.
it works.
Ground source heat pump systems aren't all created equal. There's a measurement called the coefficient of performance that indicates how well a system is working. Con Frank, in this next video clip, explains his decision to install a ground source heat pump system for his highly efficient home, and he also mentions the coefficient of performance.
Ground source heat pump is the most efficient system that the EPA determined that many years ago. That ground source heat pump is the most efficient way to heat and cool any building that there is. For every dollar of electricity that you put in to run that heat pump, we will get as much as $6 or $7 of efficiency out of it in the spring and in the fall. So it's pretty tremendous.
A specific detail, with your good knowledge, the coefficient of performance is a common means of rating air source, ground source, heat pump systems. Can you tell me where this one is performing after a couple of years of operation?
So our coefficient of performance, it varies between the 10 furnaces because they're different sizes. They range from a 2-ton rating to a 6-ton rating. But typically the coefficient of performance is just below 3.5, which means 1 part of energy to operate the system will provide 3.5 units of electricity or thermal energy either into the ground or from the ground. Well, the 3.5 pertains to heating mode.
Right.
In the cooling mode,
yeah.
the EER is a little over 13, which
Okay.
translates to close to a 4 coefficient of performance, 3.9 or something, I think.
Okay. It's
So
a little better on the cooling side.
Exactly.
But than
Yeah.
it's been doing on the heating side. Both
Right.
are pretty outstanding because, like you said, in comparison to if it was just, let's say, we'll keep it on the heating, like electric resistance heating, that's typically thought of as 1 as far as a coefficient of performance. So you're getting 3.5 times that.
That's right,
as
for
far as-
free.
yeah, for free. Taking advantage of what Mother Nature's given us
That's right.
outside in the ground, exactly.
And there are no carbon emissions or CO2 emissions or methane or anything like that. It's all zero greenhouse gases.
Beautiful.
As you've just seen, the ground source heat pump systems are major elements of the excellent energy performance of the First Universalist Church, as well as Con Frank's single-family home. There's more info about the ground source heat pump systems and our other energy efficient measures, which we just presented, on our Heart of a Building website. An airtight, highly insulated envelope, along with the ground source heat pump systems, they're the most important elements to the energy efficient buildings that we focused on. Yet there's other energy efficiency measures that also make these projects so special, including efficient mechanical ventilation, such as heat recovery ventilation, high efficiency lighting, including the lighting controls, domestic water heating, especially in the single family and multifamily buildings, energy efficient appliances, Energy Star rated, like refrigerators and dishwashers and office equipment, as well as the basic orientation of a building and the site to take advantage of passive solar benefits and be optimized for the installation of solar PV and possibly solar water heating. Keep these items in mind as you design and build your next buildings. And we plan to delve into these and other topics that can help you reach your goals of high-performing buildings in future sessions of Heart of a Building. And remember to check out the Heart of a Building website for further information on the technologies and products that help to make these projects perform so well. And remember to view the related Heart of a Building video, where Paul interviews the owners and builders who've put their heart into their exceptional buildings. Thanks for watching, and go ahead, put your whole heart into your building projects.